All right, so let's go ahead and start taking a look because most of us have already got this one actually completed. So I will say that this problem actually used to be a problem. When you went to the grocery store, hot dogs were sold in packs of 10 and hot dog buns were sold in packs of 8. They have since fixed it, and when you go buy hot dogs and you buy buns, they're both in packages of 8. Okay? But it used to be if you went and bought buns and you went and bought hot dogs, you'd always have 2 buns left over because buns always came in packages of 10, hot dogs came in packages of 8, and I have no idea why. Okay? So, this is not asking you or telling you what to find, but you need to know what you're looking for. Now, some of you may find the answer to this problem and not actually realize what the number you found represents, but ultimately what this problem becomes is a least common multiple problem. So we're going to buy packages of hot dogs. It means that you can buy 10, 20, 30, 40, 50, 60, however many, but every time you buy a package, you're going to get 10 of them. You're also able to buy packages of buns. So if you buy 1, you buy 8. If you buy 2, you buy 16. If you buy 3, you buy 24, and so on and so forth. We want to figure out when the number of hot dogs and the number of buns will be the same, so I've got the same amount of each of these. So what I saw, and it was split probably 50-50 as I walked around the room. Some of us did prime factorization. Some of us just did the list of our factors. Okay? And the list of our factors, for some of us, we actually have a content or context that we can give it to. Like 10. What does 10 represent? Well, if I bought 1 package of hot dogs, I'm getting 10 hot dogs. If I bought 2 packs, I'm buying 20. 3 packs is 30. 4 packs is 40, 5 packs is 50, and this list continues on forever. But then we can also create our list of buns. Our buns come in packages of 8. So if I bought 1, we're going to get 8 buns. 2 of them, we're going to get 16. 3 of them, we're going to get 24. 4 of them, we're going to get 32 buns. And if we buy 5 packages, we're going to get 40. So the question is how many hot dogs, one specifically, what is the least number of hot dogs that you can buy so that you have the same number of buns? And so what we're looking for is a number that is a multiple of both of these. In this case, it is 40. So I can buy a total of 40 hot dogs, and I can also buy a total of 40 buns. Then each hot dog has a bun with it. Now, how many packages of each? This is where it's going to change. How many packages of hot dogs are you going to need to buy? 4. How many packages of buns are you going to need to buy? You're going to need to buy 5. Okay, we're going to result in getting 40 of each, but that's 4 packages of hot dogs, and it is 5 packages of buns. All right, here is your second one to consider. All right, let's go. Working on this one. Brand new problem. What's that?
I just know that it's 12 because that's the least, like the most that it has.
I don't know. Maybe, So what's your answer?
4 feet.
What's that?
4 feet. 2 waters.
No, but the question should just be one number. What's the greatest number of kits that she can make? All right, so we did really well on number 1. I have 4 people with the right answer for this one. And here is the thing. Sometimes when we are used to openers, we're used to it being the skill that we just got done talking about. This is not a least common multiple problem. Because here's the most common answer I saw as I walked around, 48. Here's the problem with 48. How can you take 16 cans of food and put that into 48 different kits? Can you? No. Because if I'm going to make 48 kits, I need at least 48 cans of food, don't I? I only have 16. Okay, and the last I checked, I can't take my 12 bottles of water and cut them into 48 equal pieces. It's not going to work. So be careful. Reread this problem. It is not just automatically a least common multiple problem because that's what the previous one was, and that's what our homework was. And this is why I threw this one on here. I didn't want it to be just like, well, we did least common multiples, so he's just testing us on least common multiples. Story problems can be anything that we've talked about. We have 12 bottles of water. We have 16 cans of food. We want to make identical kits. What is the most number of kits that can be made and have the equal amount in each one? You need to go back to the drawing board, many of you. I can't make 48 kits if I don't have 48 bottles of water. All right, so let's start taking a look at this. Again, I'm not going to do the factor tree. You're more than welcome to, but let's take a look at it. If I have 12 bottles of water, and I would like each kit, however many I make, and I'll be honest, maybe I can only make one. But if I want each kit to have an equal amount of water in it, here's what I know right now. I can't make more than 12 kits. Because I have no more than 12 bottles of water. So if there were just 12 students in here and I have 12 bottles of water, that's great because I can give each of you one bottle of water. But if there's 24 of you in here, I can't give each one of you a bottle of water. That doesn't work. So we're not looking for multiples of 12. We're looking for factors of 12. Could I make one kit? Yes, I could. If I made one kit, how many bottles would that one kid have? It would have 12 bottles. Okay, could I make 2 kits? Yes. If I made 2 kits, how many does each one have? It's got 6 bottles. Could I make 3 kits? Yes. 3 kits, each one would have what? 4 bottles. Could I make 4 kits? Yes. 4 kits would have how many? 3 bottles. Could I make 5 kits? No, because 5 doesn't divide 12 evenly. Could I make 6 kits? And each one would have what? 2 bottles of water. And could I make 7, 8, 9, 10, 11, 12? Yes, and if I made 12 kits, each one would have 1 bottle of water. So these are my scenarios if I have 12 bottles of water. I can only make 1, 2, 3, 4, 6, or 12 kits. Those are the only numbers that divide that evenly. Now, I'm not going to create all of these, but if I have 16 cans of food, can I create 1 kit? Yes. How many cans would it have? 16. Can I create 2 kits? Yes. How many would each of them have? 8 cans. Can I create 3 kits? No, because 3 doesn't go into 16 evenly. What about 4 kits? Yes, each kit would have 4 cans of food. 5, 6, 7, 8, 8, and each one would have how much? 2. And then my last scenario would be if I created 16 kits, where each one would have 1 can. So the question says is, what is the greatest number of kits that can be created? Well, we have 4 kits with 12 bottles. We have 4 kits with 16 cans. The greatest number of kits that can be created is 4. Now, if I create 4 kits, each kit's going to have what? How many bottles of water? 3 bottles of water. How many cans of food? 4 cans of food. But again, my greatest number of kits in this particular problem is going to be 4. So, what our big struggle or big idea is, we're not just trying to teach you the math. Here's some computational skills, get really good at it. We want to start to teach you how to apply it. Okay? So being able to read a story problem, because here's what we've figured out a long, long time ago, and it didn't take me a long time to figure this out because it's pretty obvious. Most students hate story problems. Well, I'm going to be honest. If you're ever going to do math outside of high school, unless you're helping a younger sibling or way down the road a son or a daughter, you're probably not doing a math problem that says find the greatest common factor. If you're ever going to use math outside of high school and college, you're going to need to have a scenario to put it with. It's got to be in a story problem. And you're going to see those all the time. Okay? So we want to start to be able to apply these to different scenarios. This is what I need to be able to find. As the year goes on, it's going to be more and more challenging, because here's what I'm going to tell you. Our story problems will most of the time be tied to a skill that we've already done. But I'm not going to tell you what it's tied to. You can't just always assume that it's tied to what we did yesterday. And I'll also be honest, sometimes there's skills that we don't teach in class that you've learned a long time ago. And now it's just being able to put it into a new application. Okay? I'll be honest, one of my first classes that I took at UNI. Okay, I went to Kirkwood for 2 years, went to UNI for a year, 2 years. My first class that I ever took at UNI. I walked in, and the professor looked at me and goes, "You don't need any math above high school math." And he was talking Algebra 1, Geometry, and Algebra 2. That was it. Okay, we were all math majors. He knew that we'd all taken at least those 3 math courses in high school. And his thing was, you don't need any math above this. And you know what we had an entire week to work on every week for the entire semester? He gave us 4 problems. And that was it. We showed up and we worked on 4 problems. An hour a day for 3 days a week. And we never got 4 problems done in 3 hours. Never. I was in a group, and we had to meet outside of class to go over those 4 problems. And here was the most challenging part. He didn't teach us a curriculum. He didn't teach us skills. So what we had learned in high school was we practiced something, and then when I gave you a story problem, it had to do with that skill. So many of us, I'll be honest, you probably did problem number 1 because we had just done greatest common or least common multiple yesterday. Well, that's great, but now we got to a problem that wasn't least common multiple, but we just assumed that it was. So here was the struggle that we had. And one of the people in my group, she's an Algebra 1 teacher just down the hallway right now. Okay? But we struggled every week because it's like, how do you do this? Am I talking about an Algebra 1 problem, a geometry problem, or an Algebra 2 problem? Think about that. All of the stuff that you learn is now thrown into a problem, and you had to decipher what you had to use. There was nobody there to stand over your shoulder and go, no, don't do that. You got to the end of it and you're like, nope, that strategy didn't work. Now I got to come up with another one. It was maybe one of the most frustrating classes, but the productive struggle, I learned awfully quick, like you got to learn how to do math in different settings. It's not just solve this problem and here's the problem. Okay? Here's a real life application problem. Figure it out. All right? You might say, well, that's never going to happen to me. I'll never forget. Again, I told you guys I worked construction. Okay? Manual labor. We did numbers all the time. In the U.S., when you measure something, guess what you measured in? Feet and inches. So you know what happened one time? We were building this big, huge 15-plex condominium out by Kirkwood. You know, when they shipped everything, they sent everything in meters. Don't know why, but everything was packaged in meters. And here's if you've never, and none of you have ever worked construction, probably at least at this level, here's what you got to realize. Like when they send a board, this board can't be used for anything. It's got a specific spot that it goes in the house. And if you don't use it for that spot, you're never going to get another board until you order another one. Like, they send specific things for specific spots. So we couldn't just grab whatever we wanted and say, hey, I got a board that's twice as long as what I need. I'm just going to cut it in half and make it work here. No, that board had a spot that it had to go. So the first thing we had to do was we had to troubleshoot how are we going to get all of these things that are in centimeters and meters into what we know, which are feet and inches. We spent an entire day just troubleshooting how to figure this out because they sent us the wrong diagrams. And if we waited for them, we would have waited probably 2 weeks to get the right ones. Well, we had to get it fixed. We had a scenario, a story problem that we quickly had to adjust to. Okay? It happens all the time. You've got to have problem-solving skills to be able to get you through that. Okay? And I'll say this, I've told people this a long time. You ever go into a profession like that, and some of you guys might go, well, I'm never going to do that. That's fine. I never thought I was going to. You got paid for what you knew. Okay? So when I worked construction, by my 5th or 6th year, I was making close to $40 an hour. You're not going to find a job right now that makes $40 an hour. Why did I get paid so much? Because I knew my skill, and I knew the numbers behind it. Every year we'd get a high school kid that would come and work for us. He'd make $10 an hour. Why? All your job is this summer is to carry lumber for me. So I didn't have to do any of the hard manual labor. I got to do all the mental math stuff, and I got paid because of it. Having those problem-solving skills, having that knowledge to build off of, is really, really good. Because you make a lot more money than anybody else, and most of the time you do a lot less work. And that was exactly where I was at. Again, if it wasn't for the summers or winters in Iowa and summers in Iowa, it probably would have been a great job. But I didn't like working when it was 10 below or 90 degrees outside. So, all right. Let's take a look at your homework assignment from last night. So that should be out, page 191. We did 3 through 23 odd. We did have a couple fraction problems on here that we talked a little bit about yesterday, so hopefully we were able to adjust those some. I like those because they dealt with equivalent fractions, which is something that we had just talked about earlier. Let's see. I need to click. All right, and again, I'll scroll down here in a minute. These are just answers. So if we want to see work, we'll see work. 11 and 13. It asked which fraction was greater, and you needed to use the fractions that they gave you. Now, you had to find a common denominator in order to create or to compare them, but those are the fractions that were greater. All right, let's start taking a look. What do we got?
15.
Okay, number 15. So number 15 says, describe the error analysis in finding the least common multiple of 16 and 30. So they use exponents, but they'd already got our prime factorization down. So they have 1, 2, 3, 4 twos in this first one, and the second one was a 2, 3, and a 5. And what they said was the least common multiple, they have 2 to the 5th, which is 1, 2, 3, 4, 5 twos, a 3, and a 5. So they said that our least common multiple in this problem is 480. Okay? This is wrong. Let's determine why. When we're finding least common multiples like this, using prime factorization, what is the first thing that we look for? What they have in common to begin with. So when we look at what they have in common here, these each have a 2. Now, how many 2's do I bring down from that group? Both of them or one of them? I only bring down one of them. Okay? Do they have anything else in common? No. So again, this would be an example right here. This is a greatest common factor right here. Now, we also have to bring everything else that they have in common, or don't have in common. So 3 2's and a 3 and a 5. So if we take a look at what we should do and what they did, what do they have up here that they shouldn't have? They've got an extra 2. They brought down both 2's and not just one of them. So it should be those 6 numbers multiplied together, which should give me a least common multiple of 240 instead of 480. All right, what's another question that we've got on the homework? Monica. Number 11. So number 11 gave us two fractions, 3/4 and 5/8. And it said determine which of these two fractions is the larger of the two. So again, this is actually going to tie back a little bit into what we talked about in section 4.3. First of all, if I want to compare one fraction to another, what has to be the same? The denominator. Okay, I can't compare 2/3 and 3/4 and say one's bigger than the other without having a common denominator. So, how do I make my denominators the same here? Well, I want these both to be the same number. So what's my least common multiple of 4 and 8? 2. No, that's my greatest common factor. I'm asking for the least common multiple. Is 8. Okay, we have to understand the difference between an LCM and a GCF. Now, if the least common multiple is 8, that means I don't need to change this fraction, but I need to change this one. So what I want to do is write an equivalent fraction. So if I want to write an equivalent fraction, and I want this to be an 8, what do I have to multiply the bottom by? 2. Which means if I'm making an equivalent fraction, I have to multiply the top by 2 as well. So this fraction now becomes 6/8. And my other fraction is going to stay the same as 5/8. Now that you have a common denominator, the larger fraction simply has the larger numerator. So this fraction should be the bigger of the two. Now you might say, well, but they didn't say it was 6/8. They said it was 3/4 because they're asking which of the two is the biggest here. This is the bigger fraction, 3/4. Now, we made it into 6/8, but 3/4 is the one of the original two fractions they asked you about. That's the one that needs to be part of your answer. All right, next question we've got. Okay, number 33. Number 33, they gave us two monomials. So they weren't just numbers, they were numbers that also had variables, and asked us to find our least common multiple. So in the very first one, in 33, we have 2n to the third. And in our second one, we have 8n. All right, now if you go to create a factor tree about 2, what do you notice? It's already, well, it's already prime, isn't it? So when you go to do a factor tree of it, there's no breaking it down. So this is going to be 2 with 3 n's on it. Whereas with 8, gentlemen, if we can put that paper away, that would be great. Okay? Feel like we're passing notes back in 3rd grade. All right, 8, we're going to break into what? 2 and 4. Okay, 2's prime, we're going to leave that the same. But 4 then is going to go into a 2 and a 2. Okay, so we have 2 times 2 times 2 with 2 n's on it. So again, the first thing we're going to do is we're going to find out what they have in common, which is they've got a 2 here and they've got an n here. So 2n would represent our, sorry, they've got another n, yep. So 2n squared would be my greatest common factor. My least common multiple, I'm going to pull down my extra n and these two 2's. So I'm going to take 2 times 2 times 2, which is 8, n times n times n, which is going to give me n cubed. Now, if I think of this as like the listing idea, my multiples of 8 are 8, 16, 24, 32, 40, blah, blah, blah. The smallest of those that 2 goes into is 8. So if I think of it as a list idea, I'm going to see that 8 is my least common multiple. Now, here's the opposite thing. When we did greatest common factor, your greatest common factor for your variables, you always chose whatever the smaller of the two exponents was. So my greatest common factor is 2n squared, right? Because this is an n squared, which is smaller than n cubed. When I'm doing least common multiples, I got to choose the bigger of the two. This has 3 n's, has 2 n's. My answer is going to have 3 n's in it. So there are some similarities and differences. There's some shortcuts that you can use, but you got to know when to use which one. All right, what else do we have? Any other questions? Least common multiples of numbers or monomials?